Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Geoff Tate of Flex Logix. I'm going to talk today about eFPGAs and how the conversation around eFPGAs and the questions being asked have changed. Geoff, over the past year, we've been talking about eFPGAs, and they've sort of been a little slow out of the starting gate after some real strong initial interest. What's changed?
Adoption is accelerating, and that's changing what customers are asking for. In terms of being slow to the starting gate, when I did Rambus, it took us 5 to 6 years to get out of the starting gate. We've been doing embedded FPGA for a little over 5 years now, so it's starting to hit stride just like it did at Rambus.
Is there anything in particular that's changed to alter how this is rolling out? I mean, why now versus, say, a year ago, 2 years ago? It always made sense in terms of add programmability into an ASIC.
It did always make sense, but 5 years ago, people had actually tried other folks for the last 20 years and had been burned. So there was reluctance to engage, risk avoidance, and we had to find the few brave people who were willing to try it and like it. And as they tell their friends, more and more people are willing to try it now that it's become a proven technology.
So why don't you draw this out for us?
Sure.
So Geoff, what's the big change here?
The big change is that we're over our experimentation period. I did a startup called Rambus, and that was a big success, but it took years for customers to get comfortable with the technology. And the same has been happening here. So we've had some early pioneers, they've had successes, they've shared those successes, they told their friends. The value of embedded FPGA has always been clear. The question was whether it would work. Now that they see that it works, we're getting growing adoption. So we've got now over a dozen working chips out in multiple nodes with multiple customers, and we've got dozens more in process, in fab, in design, and in evaluation. So we're seeing the commercial activity taking off, and our revenue stream is in the double-digit millions of dollars now.
One of the problems with eFPGAs is people really do have to understand this is not just adding simple programmable logic into a SoC or an ASIC, right? It's really, you have to think this through as part of the architecture.
That's true. We have two different sets of customers. One set of customers are already using an FPGA chip, and they want to integrate it inside their existing ASIC when they go to the next process node. So in that case, they've already got an architecture. They know what blocks are in the FPGA and what blocks are in the ASIC. And so for them, it's more straightforward. For our customers who want acceleration or want flexibility and have not used FPGA before, it does take them some more time to think through how best to use it.
Is part of this also the fact that people are finally getting to understand that the algorithms are changing so fast, they really do need some kind of flexibility built into the ASIC model? It's just too hard, too expensive, and too time consuming to be able to change all the stuff around.
Yeah, different applications are different, but there certainly are a number of applications where people believe that they will need to change algorithms during the life of the chip, and that's easiest done by having a very programmable FPGA element.
And some of this stuff is coming down into the most advanced nodes now too, right? I mean, we thought about when we looked at eFPGAs, a lot of the people that were kicking the tires were working off of some of the older nodes.
Yeah, if you go back 5 years, there was this chart was almost blank. And the very first node we worked on was 28 nanometers. And that was an advanced node at the time. But now we're going down into 7 this year.
What's different about an eFPGA in 180 versus 7? What do you, even 28 versus 7, what do you have to keep in mind there? Is it the same as you would deal with in just shrinking devices all the way down, or is there more to it?
Well, actually, that's a good question, because the embedded FPGA that we designed for Sandia Labs, which is their fab, has a 180 nanometer process. architecturally, it's the exact same eFlex 4K tile as we've designed on 28 and 22 and 16 and 12 and now 7. So we've implemented the same architecture from 180 down to FinFET. The size is much smaller in FinFET, but it's the exact same architecture and programmed the same way.
And you're still dealing with the same moving the electrons around. You still have to get them through wires. It's still the same challenges that you would deal with in any design, right? So you put in a block in 7 nanometers, and it's still going to be the same challenges of we have RC delay, we have the parasitics. It's the same issues as you would deal with any other circuit.
Yeah, but the design complexity goes up with the FinFET processes. The run times are longer, the number of DRC checks are more, but the concept is the same. It just takes more engineering work and more CAD time with the advanced nodes because of all of the complex multi-layer patterning.
Because this is programmable logic, does it require more cooling because you generally use more power to run a programmable circuit than you do a hardwired one?
Well, no, that depends on what the customer wants, which is one of the things we'll touch on in a second. So originally, most of the customers were talking to us about give me the fastest thing you can. If you look at Xilinx FPGAs, they're not known for being small or low power. People want maximum performance. But we do have customers now who are power sensitive, and they ask us to turn the knob the other way. And we take the same architecture. Architecturally, it's the same, but instead of having the ultra low VTs that give you super high speed and high power, we switch, for some cases, all the way to very high VTs, which give us much lower power, much lower leakage, but of course, cost on frequency. So we can tune it to meet the customer's objectives.
So what are the main applications for this?
We're playing in a lot of markets, but when you look at where the customers are coming from, it falls into 3 categories. There are the customers who use FPGAs now, and they love FPGAs, but they want a lower cost, they want a lower power. In some cases, like if you're putting it into an airplane or a satellite, size and weight are also important. So they're looking to integrate. The other sets of customers are people who do not use FPGAs. They're not familiar with FPGAs, but want increased flexibility because algorithms are changing, or they have workloads that are important to them that work better with the parallel execution of an FPGA. So those are the 3 types of applications, and the kinds of markets we're in is aerospace, communications, mixed signal, consumer, so a range of products.
Is any one of these a standout, or are they all 3 of them starting to grow?
The first adopters were in the first category because we didn't have to convince them about FPGA. But they knew that if they could integrate it, they would get a better solution. So all of our early customers were people who use FPGAs a lot. And if you look at our public releases, it was folks like Sandia Labs, DARPA, Boeing, so aerospace people. 1/3 of electronics bought by the US aerospace industry are FPGAs. So they love them, but they want them lower cost, lower power. And for many of those customers, they want them made in the United States, which is why we have a global foundries 12 nanometer port. But in the commercial marketplace, most of our customers are not using FPGAs. They're looking to use embedded FPGA for flexibility and or acceleration.
A lot of this going into AI type of chips?
No. AI chips are going to be, there's going to be a class of products which we're developing one, which will be much better than FPGAs for AI. And we have an optimized embedded FPGA that's going into our own chip that we're taping out now. But it's highly optimized. It's different from the kind of embedded FPGA that's similar to what Xilinx uses.
There's also been a big push over probably the past couple of years from sort of moving from a standard, we have a chip and we're going to build a platform around the chip, to we're going to customize for a particular customer set. How does that play into the eFPGA world?
We've been doing embedded FPGA for about 5 years now. So for the first several years, it was hard to get customers to commit because of the risk issue we discussed. And to make the economics work, we had to design an embedded FPGA where I call it one size fits all. We could do a 4,000 lot array, or we could do a 400,000 lot array. But now we're engaging with multiple customers who come to us and they plan from the start to do multiple chips. So if they're doing multiple chips, they've got a bigger budget, and we can optimize the FPGA to meet their specific needs. Okay. And some of them have very high volumes, millions and hundreds of millions of units. And again, with high volumes, their budgets are different, and so we can afford to invest extra engineering and optimize the FPGA for different segments of the market in ways that we couldn't justify in the first few years.
So you're starting to get the real economies of scale for how you're applying your engineering resources for your customers.
Or to flip it around, the customers are asking us, can you do X? And we tell them, yeah, but it'll cost more. And they say, no problem. Whereas in the past, it was, hey, I want to keep this. I'm going to do one chip. It's kind of a toe in the water. I want to keep the budget low. I'll worry about optimizing later. So now they like it, and they're moving to the next phase.
So what are some of the real world examples you're seeing out of this?
Okay, there's three that we see from different customers, and every customer has different trade-offs. So like I mentioned, the initial demand for FPGA, embedded FPGA, was give me maximum performance, because these were people who were using Xilinx and Altera arrays, and those are optimized for speed over power. But now we have a set of customers who ask us, hey, can you optimize the power? In the end, what everybody would like is super high speed at zero power, but you can't do that. But through various circuit changes, we can change the mix between speed and performance. So the three things that we can do, and we do this without changing the architecture, is we can use high VT transistors, which cut leakage power, because the low power customers tend to be very sensitive to leakage power as well as dynamic power, but it cuts performance as well. But for a certain set of customers, this is very attractive. Think people like microcontrollers. Another one is power modes. In some applications, they're only operating part of the time, and when they're not on, they want to draw very low power. So we can do circuit tricks, which we've done in the past, like in 40 ULP, where we can retain state, go into a deep sleep, low power mode, wake up quickly, and go back into full speed operation. And with certain processes, we can even offer body back bias options for further optimization. So we can deploy all these tricks, and different customers ask us to go to different levels. There's trade-offs in these, so it's not a simple low power, high speed. There's a continuum in between. So this is one of the areas that we're optimizing for certain customers.
Some of your markets, though, you really have to be almost bulletproof with this stuff, right? Because you're thinking about Mil-Aero, for example, they want extremely high reliability. They've been asking for that for a long time. That's same in automotive, medical, all these other new markets that are starting to develop. How does that play in with what you've got here?
Well, that's the second area, Ed, that we're having customers ask us to do optimizations. The three markets where we see high reliability as extremely important is autonomous vehicles, space applications, and medical applications. So high reliability means it's even more important than normal that there's never a mistake. And the reality of semiconductors is that semiconductors have ever smaller storage units that can flip when a cosmic ray hits. That happens if your PC goes crazy. It might be because a cosmic ray hit the address counter and it's off executing in the wrong space. So you reboot. If you're out in space, or if the car is driving itself, you really want to avoid those kind of issues. So how do you get high reliability in an FPGA? There's scrubbing, where you go in and you read out the bits, you check them, you fix bad bits, and you write them back. But that doesn't protect you for the cycles while you haven't, you'll still have a fault. So that's not really acceptable. So for these markets, either we do triple redundancy on the storage. For every flop, instead of having one flop, you have three flops, and you have an exclusive OR. So if one of them flips, you'll still get the right value, and then you have to sense that it flipped and go back and write it. So if the second one was to flip later, you're okay. That's pretty expensive. That almost doubles the size of the array. The other alternative is rad hard, where people, not us, design storage elements, knowing the characteristics of the radiation that they're dealing with in order to get a much less likely to flip storage element. They give us the cell library and we use that to design our embedded FPGA. So we have done high reliability designs now on 2 different process nodes, and we're working on more.
Triple redundant storage was what they used to use in satellites to prevent things like tin whiskers from forming and shorting a circuit. Rad hard was basically just when they would put things into military applications like missiles. They wouldn't decompose it as the heat rose or get cold, right?
Yeah, we're not experts in rad hard. We take cell libraries from foundries and we use them. So if the customer says, "Hey, this is a rad hard cell library," to us it's a rectangle with inputs and outputs. They don't show us the inside because that's secret stuff, and we go from there. But if you look at people like Tesla in their cars has 2 of their processors, so they do not have triple redundancy because it's not fully autonomous. If they detect an error where there's a mismatch, then it cuts out and the driver has to take over. If you want fully autonomous, the way to go is to either have triple redundant storage, or what you can do is you could have 3 copies of your embedded FPGA and have voting logic on the output. Like they use, it goes way back to the Apollo series. There are 3 computers on there, and if 2 of them disagreed with the third, the 2 in majority won.
Yeah, all this has to be price competitive with the other options that are out there. Where do you fit into that curve?
Yeah, well, we have a set of customers who are planning to build a lot of chips using our technology. So those customers are now asking us, what can you do to take your design, which was good enough to get started with, but as the volumes go up, saving every penny matters. And they're asking us, can you make the design smaller? 10%, 20%, 30%. Tell me what you can do. So we use standard cells for design. And the reason we can use standard cells is that my co-founder came up with an interconnect that's twice as area efficient for traditional FPGAs. So Xilinx, they design FPGA, they have 50 to 100 full custom circuit designers. We do our work with 4 or 5 engineers in 6 to 8 months. But we can start to employ some of the tricks that are used in the big guys FPGAs. For example, number 2 here is our current 16 nanometer. We just use 7 metal layers, but many of our customers are using all the metal stack on 16 nanometers. So they've got like 14 layers of metal. We've just got 7. So they say, hey, well, what would happen if you optimized your 16 nanometer and you use more stacked layers of metal? Well, the answer is we could pack the standard cells more closely together, reducing the area. And the extra metal layers don't cost them anything because they're already using the metal layers. Now, the reason we didn't do that in the first place is every customer uses different metal stack. If we pick a metal stack where we're using all the layers, when the customers come to us, if they pick some other metal stack, they can't use us. So this only makes sense when you get really high volume. But increasing metal layers can cut the area 10 or 20%. Another one up above is our current FPGA. We can take the 1 tile and we can build 7 by 7 arrays, 8 by 8 arrays. So our interconnect inside that 1 tile is really geared not for a small array, but to build a very large array. It's like having an 8-lane freeway in a small town. You don't really need it if you're not going to build big arrays. But we did it that way because then we could do one design and cover a wide range of the market. So we can take interconnect resources out of our tile if a customer tells us, hey, the biggest array I'm going to build is 3 by 3. We can take out 20% of the circuitry. It won't be able to build an 8 by 8 array then, but for them, we can cut the size 10, 20% and make them very happy. And something else we can do at some point in the future is look at full custom circuit design to get even further reductions in area. Taking blocks of our logic and creating specialized cells, not just using standard cells. That's a much bigger investment, so it's not one that we've done yet, but we are working on the first 2 for certain customers.
So the bottom line here is this is customizable in many different directions.
Yes. Yes, and some customers want us to do combinations of all three of these. They give me rad hard, give me low power, make it smaller, or etc. So if they're willing to pay more, we can take our design, which they already like, and make it even better to suit their needs.
Geoff Tate, thanks for a great explanation.
Hey, Ed, great being with you again.